Good morning. Welcome to our webinar today, Reducing Corrosion Risk with Accurate Phosphate Monitoring. My name is Dominic O'Donnell. I'm the Marketing Director here at Swan USA. And in just a moment, I'll be handing off to our presenter, Ryan Richardson. Before I do that, though, I want to familiarize you with the software we're using for today's webinar, GoToMeeting. You should see our welcome slide with the title page of our webinar currently. And in just a moment, we'll be going to the next slide. And on this, you can see the control panel that hopefully is also visible in your window today. This will allow you to reach out to us with any questions or comments or feedback as we go through the webinar. You are currently muted to prevent any noise or distractions for the rest of the attendees, but we do hope to hear from you through the question panel. Our speaker today, Ryan Richardson, has been a water professional for almost 30 years and has been serving as the regional sales manager for Swan in the Southeast most recently. And with this, I will hand it off to Ryan. Take it away, Ryan.
All right, thank you, Dom. Welcome, everybody. Again, as Dom said, my name is Ryan Richardson. I'm the Southeast Regional Manager here for Swan Analytical, and I'm happy to be a part of the call today. This is our introduction slide. It tells a little bit about what we're going to be doing. First, we're going to talk about lead and copper, a little on corrosion, how that happens in our systems, some of the methods to control it, methods of measuring it, talking a little bit about some of the benefits of continuous monitoring, and then we're going to talk at the end a little bit about Swan solution for continuous monitoring in our AMI phosphate. So let's talk a little bit about the lead and copper rule. Most of you are familiar with this, but for those who aren't, or we all need a little refresher and thinking about why it is that we're even talking about phosphate, lead and copper enter our drinking water through our plumbing materials. So we have focused so much on our plants, and honestly, we're asking our plants to do incredible jobs to comply with the levels that we're talking about for water quality. And then we release our very good water into the distribution system where it's subject to all manner of things. And one of those things is the inside of pipes. So lead and copper pipes can leach out into the water, and exposure to those things can cause health issues. And we're all familiar with some of the stories that have made national news recently as to what the problems that can cause. And in 1991, the EPA established our current lead and copper rule. And this is an excerpt from it. If we exceed an action level of 15 ppb of copper concentration and 1.3 parts per million and more than 10% of customer taps, then we've got to take some actions to control corrosion. So we're all looking to get out ahead of the game on those things. And so let's talk a little bit about what the problem is. So the problem is corrosion, which is anything that looks to break down material by either chemical or electrochemical reaction with its environment. So this is a little graphic of electrochemical there. You can also have just strict chemical attack, and then we also have microbiological attack, which can cause corrosion if there's enough oxygen, and sometimes in the absence of oxygen. So this is a diagram on a little bit about what the electrochemical process is. So we've got electrons flow from one side on the metal pipe surface to another. And you can see on the right here is our anode. So if you can picture a probe that you might have in your lab or in a process, and you can know where the anode is on that. So the anode's where the oxidation occurs and the electrons are lost. And then the cathode is where the reduction occurs, where the electrons are accepted. So this is actually happening at multiple places in the pipe. So when water is exposed to in the lead and copper and the things that we have that are naturally in our water, this is what can happen inside an unprotected pipe. So our source water chemistry can influence our risk. Some places are more susceptible or develop corrosion faster than others. These are some of the things that decrease our risk. So we have a high pH can protect our water. Of course, we know that running the pH higher can cause some of our other problems from occurring. We can run into trouble with disinfection byproducts by running our pHs too high. Our alkalinity can help form protective coatings, hardness, and then chloride and sulfite, high levels increase corrosion in iron. And then increased corrosion risk, or if we have a low pH, DO, obviously, anytime we're supplying oxygen or we get areas in our distribution system that are subject to higher dissolved oxygen levels, we can have increased rates of corrosion in those particular areas. We'll talk a little bit more about that later. Chlorine residual and then high total dissolved solids can increase our risk for those things as well. So here are some of the methods. So that's our problem. We've got water and we've got metal pipes, and so we have the possibility for corrosion. So we've got to do something. So here's some of the methods that we can use. There's pH adjustment. So we can use our pH to try to get in the sweet spot for minimizing risk. But again, that impacts our disinfection. So when we get outside our pH ranges that we want to operate, we can affect the ions that are formed, and we can become either better or worse at disinfection, and of course, disinfection byproducts. So you can use calcium or carbonate adjustment, but it's important to note that calcium carbonate, it doesn't adhere well to lead and copper. So while this is an inexpensive method, it doesn't necessarily, it's not very effective. One of the best methods for reducing is to reduce our dissolved inorganic carbons. So let's try to actually get rid of the things that are causing the corrosion, aeration, lime softening, ion exchange. The problem with these things is they're expensive. So the cost of doing these in with any kind of scale across a distribution system is just, for almost every system, even the largest systems, is cost prohibitive. So what comes next? So we've got these inhibitors. So we've got orthophosphate, we've got orthophosphate blends, and these actually do a pretty good job, and they're not very expensive. So they do a pretty good job, and it's something that we can actually afford. So let's look a little bit at what phosphate, the use
Ryan?
for it in potable.
Excuse me, Ryan. We wanted to pause just for a quick moment to poll the audience. Sure. And what we'd like to know is, what method do you currently use for corrosion control? Please pick whichever one you're currently using. You can just click that and put in enter, and we'll get that. Pretty good. We've got about a quarter of the folks attending, now up to about a third. Give it just a few more seconds here. Okay, we've got.
We appreciate this. This really helps inform our discussion. It's great to see some of the methods that people are using.
We're going to close this out and then share the results with you. So from our attendees today, just under half are using phosphates, and about a quarter are either using pH or they're not controlling at all. So I'm going to hand it back over to Ryan, and he'll talk a little bit more about phosphate.
Thanks, Don. So phosphates, as we just mentioned, they do a pretty good job, and they are generally affordable. There are many different types of phosphate blends supplied by some of our water treaters. And I can get a little bit of lag after I pull there. So iron corrosion reduction we talked about. So one of the things it does is we reduce our iron corrosion, but the other thing, one of the side benefits of phosphate is we actually bind up and sequester some of the iron and manganese, which can help for color control and scaling, and our favorite red ring complaints that we get occasionally from customers. And actually, I think it's kind of funny, this is some data from 2001, and the 2001 data showed that a little over half of water utilities use phosphate. It's kind of interesting. That's, I think, Dom, that if I'm not mistaken, that's about what our poll just showed here from our attendees today. So
it was fairly close.
So interesting that 18 years later, the data is about the same, or at least for the people on this call. So this is some macro data that we've collected, and we see there can be a lot of cost savings by doing this, and we'll talk a little bit about it. The important thing, 4 billion, kind of certainly a hard number to dissect. The important thing, I think, is when we looked at the macro data that was provided, you get about a 20-fold return on investment. So this is the key thing, to remember about phosphate controls. It's not very expensive compared to what it can do for us. And reducing corrosion not only keeps us in line with our lead and copper rule, it saves us big stuff down the road. So this is definitely a preventative method, and can save us from having to do some very serious heavy lifting later when it comes to our distribution system. Let's talk for a minute about the type of phosphate. So people who are using phosphate probably already know some of this stuff, but if you're not, there's a couple different types of phosphate. So we've got orthophosphate, and this is what orthophosphate looks like on a molecular level. And then we've got condensed, or what we call polyphosphate. So we get several of those units chained together. And the poly and ortho blend is typically what we would see. So if you go to a company like Nalco or ChemTreat or G-Bets, any water treater, they more than likely are going to have their proprietary blend for what they would call a polyphosphate or an ortho blend. And what that is this basic phosphate blended with some other things. And the reason we do that is because we're always balancing the amount of phosphate or any additive, lime, anything that we put in the water, and how that is affecting our water quality. So it would be nice to just be able to dump in whatever we need to accomplish what it is we're looking for. But we're, as we all know on this call, we are constantly battling water quality versus, and what our customers are expecting versus what we are trying to do to either protect our system or stay within the limits we have for water quality. And then many of our systems and many people on this call are actually, the EPA guidelines are just a starting place, and we're looking to produce much better water. So this is a cutaway of how these things look on the inside of a pipe. So many of you have seen this either in demonstration or in your own system. So the phosphate film that we'll talk a little bit about how this works in phosphate, but it forms a film on the inside of pipes, really any metal, and is very insoluble to phosphate salt. So it does a pretty good job of hanging around. So not only does it coat the inside of the pipes, but it's pretty sturdy once it gets there. So this is the middle picture there is actually shows how that cathode and anode works on the inside of a pipe. So there's actually many, many places along the pipe where this is happening, where you have part of the pipe is acting as a cathode, part of the pipe is acting as an anode, and you get the reduction and addition of electrons. And actually inside our pipe, our water is acting as the electrolyte. So like a pH probe or something like that, we may have a refillable pH probe where you're putting KCl inside a probe as a conductor. Water is actually our electrolyte in this case. So it's both making both our end product and making things worse all the time. So that's how that functions inside. And then all the way to the right, this is what we're trying to avoid. So this is a pipe heavily corroded. You can even see the dust down there at the bottom just by setting this pipe down. That's a lot of iron, and this is obviously not acceptable for delivery of water. So how do we measure it? So we've talked about the problem. The problem's corrosion. We talked about some solutions, and at least for the purposes of this call, we're talking about using phosphate as an effective and economical way of controlling corrosion. So now we're putting phosphate in our system. We've got our coupons out in the system that we're going around and we're collecting. We're looking to see how are we doing long term for corrosion control, but how are we doing on a daily and hourly basis to make sure this phosphate that we're putting in the system, is it getting where we want it to go at the levels that we want it to be? So we use a measurement method, and it's a colorimetric method, and not unlike any of the other methods that we use for chlorine or any other colorimetric iron or manganese tests that we're using. So the orthophosphate reacts and forms this blue color. So you may be, if you're feeding phosphate, and even if you are not doing process control, you're probably running this test in the lab once a shift, or maybe even once a day, where we are taking the sample, mixing it with some reagents, and forming this blue color. And the color intensity is proportional to the phosphate concentration, not unlike the pink color that's formed when we're testing for chlorine. So this is the same, and then we read out in milligrams per liter or ppm. So the same type of measurement that we're using for a lot of other stuff. So the reason we're pointing this out is this is not a new method for measurement. We're just applying this to phosphate, and how could we use this very tried and true method for making sure that the phosphate that we're putting in the system is getting where we want it to go. So this is a little bit about really how any colorimetric method works. We have at the top there, we've got a zero measurement. So that's just the sample with nothing added. And then we have the sample right just below that with some chemistry added to it, some time allowed to react. We shine a known light source on the left there through the sample. And then what we get on the other side on the photoreceptor, the difference between what we shine through and what we get on the other side is the intensity received from the light, and that is with an algorithm relatable to concentration. So let's say that we decide, you know what, monitoring is a pretty good idea. Where might we think about doing that? So the final effluent, basically where we're feeding our phosphate, we want to make sure leaving the plant, we have a target range for phosphate, and what is that, and are we staying within it? So we have it leaving the plant, and then we've got in our distribution system. So it's great leaving the plant, everything's in spec. You know, we go to our tanks, and now we start flowing through pipe of various ages and various materials and various stages of quality as far as the integrity of the pipe. And so there may be multiple places in the distribution system that we want to check to see that our phosphate levels are what we think they ought to be. So how are we doing that now? We have crews going out, we're collecting, we're measuring, and what we're proposing and talking about in this call is that there is a different way of doing that, which is to actually put an online instrument in place.
Okay, Ryan, we've launched a second poll, and we're just asking our attendees today if they are using phosphate, how are they monitoring phosphate? And we're getting a few answers already. We'll wait about 10 or 20 seconds to get the rest of the folks a chance to join in here in the discussion.
Sure, I'll grab a sip of water here.
Okay, we've got about half of our attendees that have voted. Give it just 2-3 more seconds, just a quick click if you want to join in. And we'll go ahead and share the results. What we're seeing is that grab samples seem to be the most common method, or not monitoring at all. About a quarter of the folks that we're doing this are doing it online. I'm really interested in that no, but we've monitored in the past. If if you don't mind, if you could just shoot me a quick comment through the question box as to why you stopped monitoring, I'd love to have Ryan address that at the end of our session today. So with that, I'll hand it back over to you, Ryan. Thank you.
Thanks, Tom, and thanks for the participation in the poll there. So that's not uncommon that we see. So we're, by and large, most people, I would say, that are feeding phosphate, my experience in the field has been that we're doing grab samples. So we all know grab samples are fairly easy to do, but they give us just a little snapshot of what's going on when we take it. And we'll look at a graph that shows some of the difference of that. So we're looking for monitoring online as a live stream of what's going on all the time versus someone going out and taking a picture and bringing it back and saying, we think this is representative of what's happening in our system. So this is the Swan Amy Phosphate Analyzer, and we'll dig in a little bit to some of those parts. The measurement range is 0.01 to 10 ppm. There's the reproducibility. It's very, very accurate. We take an automatic 0 before each reading. We have both sample flow and reagent level monitoring, so we can tell that the instrument has flow, and we can also tell the sample levels, and that's a very, very important feature that's unique to Swan, in that we can tell if the instrument has flow, which is very important for remote install locations. So at this instrument, we'll talk a little bit about that in a minute. We can have a user selectable measurement frequency. So this instrument doesn't have to run wide open all the time. And frankly, if we've got a big tank that we're monitoring phosphate levels of that tank, do we really need to know what the phosphate is every 5 or 10 minutes? Probably not. The phosphate level in that tank is probably not going to change that quickly. Well, with our analyzer, you can actually push that measurement interval out. And what does that do? That saves us reagents. So we can push a measurement level out to something that tells us the information we need, but we don't get more data than we need. And we reduce the amount of money we spend on reagents, and really more importantly, the time that it takes for somebody to go out there and change it, which tends to be much more expensive than the reagents themselves. And we use an LED light source, just like the LEDs we have in our homes and cars. You're probably looking at an LED right now, whether you realize it or not. And it's a long life light source, so we cut down on having to change the light sources like we have with some of the traditional analyzers in the past. A little bit of a lag here. Here we go. So let's dig in just a little bit. I wanted to highlight a couple of the parts of the analyzer. If this is the first time you're seeing it, you see down there on the bottom, those are the reagent containers. Those are smart dip tubes that you see there on the top. So you see we have the small tubing is the delivery part, but then you see the connection there at the top of the unit. So there's actually a float switch in those reagent tubes. So we don't measure, no Swan instrument measures our reagents based on a counter or based on time, where you say, hey, I just filled reagents, and then the instrument counts and tries to take a guess at how much reagent is left. We measure the actual reagent volume and alarm off of that inside the unit. So it's a very, very accurate way to be able to know exactly how much reagent is in your containers. I wanted to highlight our reagent and sample delivery system. So this is essentially a peristaltic pump that we turned inside out. So the rollers are on the outside, and you can see that we have these preloaded clips, so there's no more rebuilding of reagent pumps, and you don't have to find a way to supply air to the instrument or have an air pump that has to be replaced or maintained to drive reagent delivery. This is a very simple, very robust pump, and we'll look at those clips there in a minute as to how those get changed. This is the constant head chamber, so we bring the sample into this head chamber and use it to fill the instrument. And then there's a close-up of the photometer, and you can see there on the bottom, that piece on the bottom is actually a bubble detector. So that's how we are measuring that the instrument has flow. And should this instrument ever lose flow, the instrument will alarm. That can be output to a SCADA system to show that the instrument has flow or does not, and we'll stop pumping reagents. So no more the instrument loses flow and we continue to chug a bunch of reagents through there and gunk up the inside of the analyzer and waste money on chemicals that we're not using. And this is a close-up of our transmitter. You can see it's very basic, very easy to navigate, just 4 buttons, and it's very easy to read both passing by and the information that's displayed. One of the things I really like about our analyzers is that if there is an error code, we display that error in plain English. So no more having to go find an AM manual and look up and see what E035 means. We actually display the code in plain English on the transmitter, which is very helpful. So let's look at a couple of the features of the instrument. So all the regular service is performed right in front of the instrument. So that panel, the instrument, that's exactly how it comes. There's no reason to have to access the back of that panel for any reason. We don't have tubing that disappears up inside, plastic housing. Everything is visible right there in the front. Reagents are very easily accessible. And I talked about the easy tubing replacement with no tools required. So you can see this is a picture of us taking these preloaded, what we call paraclips, off of the front of the analyzer. And you can see, if you can see my cursor here, these 2 little ferrules here at the bottom, you unscrew these 2, you pull the old paraclip off, you unscrew these 2 ferrules to the new tube or the new paraclip and replace it back on. It takes about 5 minutes to do. That's done twice a year, and that is the only scheduled preventative maintenance part that needs to be replaced. So there's no tubing kits, there's no pinch plates, there's no air pump to maintain. That is it, and it is a real, I don't want to say joy to work on this instrument, but it's very nice knowing that that is the only wearable part on the instrument. And then we've got a YouTube channel that actually shows maintaining that, and maybe we can send the link out to the attendees here. So this is a little bit about the fluidics of the analyzer. So we talked about the constant head fills up and the sample flows down into the measurement chamber, the photometer, for our 0 measurement. Then we call Oxycon, that's our branded reagent that is fed into the sample, causing the color reaction to begin. Then the sample enters the photometer for measurement, where the reaction completes and out's a drain. Then we flush everything out and get ready for the next cycle. And again, that cycle is user definable. So this could perform this measurement and then wait 30 minutes and do it again if that's all we needed for data. So some of these benefits of continuous monitoring are things we already know. We can adjust the feed rate when production rate changes. We'll look at that. So as our flow from our plant changes, we can automatically change our phosphate, and we can adjust the pump when performance degrades. So if our flow goes down, then we can change that down. Or if our pump starts to slow down, we're not supplying, we'll know exactly what that value is. So we can alert operators for decreasing phosphate residuals. And if you don't have a SCADA system where this instrument, if you don't have feed, but you do have a pump, this instrument can actually control a pump directly. And if we don't have a SCADA system to alarm, there are relays and alarms inside the analyzer that can actually flash lights, call cell phones, and make all kinds of noise when we're outside our control parameters. So we get a higher level of protection against corrosion by knowing how much phosphate is in our system, not how much phosphate is at the feed site for phosphate. And we can identify some of the issues that grab sampling will uncover and automatically control our phosphate feed. So we are going to look at a chart here. We have some potential cost savings, and then we may also find we're not getting enough phosphate into the system. So we'll know both of those. So here's a chart that shows an example of a manual versus automatic phosphate feed using our analyzer. So here's the flow in our plant as the day goes along. This is the line showing manual feed. So you can see as the flow goes up and we're in manual mode, our phosphate levels drop off. And then this line shows the same flow with an automatic, with an online analyzer and controlling the feed automatically. So we see that we stay much, much closer to our target level of phosphate residual. Here's an example from a plant of cost savings. So we see our MGDs there on the left, our part per million product feed, our target concentration, and then this shows at manual dosing at $2 a pound what it would cost us in phosphate. Then we see in automatic dosing with a 10% flow variation, which is very conservative. And we see here on the right what we can save. And even on 10 million gallons a day, that cost on the right there is more than enough to pay for a phosphate analyzer and have money left over. So the payback on these analyzers are very short if we're able to adjust the feed to what it needs to be. So summing up a little bit about what we talked about today, our lead and copper corrosion control we know is very important. Our pipe corrosion control is important to reduce our cost of having to replace pipes out of cycle. Right now, about half of everybody's doing that. We also we have some side benefits of that where we get to bind up some iron and manganese and make our customers happy with better water quality at the tap. Continuous monitoring, I think we can agree, is preferred over snapshot or grab sample monitoring if we have an instrument that's affordable, that is easy to maintain, and the quality of the instrument is such that we know we can be confident in buying the instrument. And this analyzer from Swan like all of our other analyzers, comes with a 3-year in-field manufacturer's warranty. So that means if you buy a Swan analyzer, you get a 3-year in-field manufacturer's warranty, no service contract required. And that is inclusive of labor and travel and parts for any manufacturer's defect. So for the first 3 years of owning this instrument, you know that you are covered. And there's only one instrument that we make that doesn't have a 3-year warranty, and that's our EPA-approved white light non-contacting turbidity, and it has a 4-year warranty. So you get 1 more year on turbidity. And then automated control of phosphate, we can reduce our chemical costs. And it has the potential to do that. It's also possible that we may need to put more phosphate in the system, but we are going to know exactly where we stand. And ultimately, that's our goal, is we want to know what the level is in our system, and is the phosphate making it to where we want to be.
Very helpful. Unless there's any other questions, I think we'll wrap things up. I'll just hold us open for another 10 seconds, 20 seconds or so, see if anyone has any further questions. And I guess with that, I just want to say thank you, Ryan. Really appreciate your sharing your experiences with us today. Thank everyone that attended today. And as mentioned, you'll be getting a thank you email along with a survey request and access to the materials that we covered here today. Feel free to reach out to us if we can be of any help to you in any way with phosphate or any of your other water quality monitoring requirements. Thank you, and have a good day.